So the last screencast, we talked about the notion of how we classify circulations into different categories based on their scale, specifically their temporal scale or their spatial scale. And the reason that was coming up when it did is because it turns out that for circulations at different scales, the way that our main forces that drive the flow, i.e. our PGF, our pressure gradient force, and the Coriolis force, the way that these forces interact is very different for circulations at different scales. So for instance, the way the pressure gradient force and the Coriolis force interact in a small scale turbulent eddy is going to be very different from the way they interact in a large scale planetary circulation, say. So that's what we're going to start talking about now. That is how these two different forces interact with each other. And for the next several screencasts, we're going to focus mainly on large scale flows. That is the synoptic scale and the planetary scale. Because if you remember from the previous screencast, it's really these large scale flows that determine how our day-to-day weather evolves. So if you want to understand how day-to-day weather works, you really have to understand how circulations behave at large scale. Okay, so what's the deal? So how do the pressure gradient and Coriolis forces interact at large scales? Well, it turns out that large-scale flows have an interesting property, which is that when you go and you look at large-scale flows, you typically find that, for our synoptic and planetary scale flows, when you go out and take measurements of these things, you typically find that your pressure gradient force and the Coriolis force are often very nearly in balance. That is, they're very nearly canceling each other. That is, so if you have the pressure gradient force pointing or pushing in one particular direction, say, typically what you'll find is that the Coriolis force actually pulls in the other direction, and it pulls roughly with the same strength, so that the two pushes and pulls are basically canceling each other into nothing. So why would that be? Why would that be that these two forces are essentially in balance for large-scale flows? Well, the reason is that the large-scale flows were really slow. If you remember, they're the flows that evolve over time scales of days to weeks or even longer. So they're really slow flows. It takes them a long time to evolve. And because of that, there's a lot of time for these forces to equilibrate. So if they're not quite in balance, then they'll eventually come to sort of an equilibration where they'll sort of balance each other out. So that's the basic reason. Because they're so slow, then there's time for these forces to come into sort of an equilibration, to sort of balance each other out. Should note that this isn't true at smaller scales. So if you're looking at flow at mesoscale or at the microscales, those flows evolve more quickly. And so as a result, there's not the time necessary. So there's not enough time for these forces to equilibrate, to come into a balance with each other. Now, I should say that you could also make the argument the other way. That is, the reason that the large-scale flows evolve so slowly is because the forces are essentially canceling each other out. So there's not a whole lot of net force left over. And so the net force that's driving those flows is really small. And if you don't have much of a force, then the changes that you produce are going to be really slow. So it's you can look at the causality in both directions, but they're consistent, right? So the flows are slow, the forces come into balance, and because the forces are roughly in balance, they're slow. So it goes both ways. Okay, we're going to draw a bunch of pictures of this on the next few slides to see how this works. But for now, let's give it a name, because it turns out that this rough balancing of the pressure gradient and Coriolis forces has a name. So this balance between the PGF, the pressure gradient force, and the Coriolis force, this guy has a name, and it's referred to as the geostrophic balance. Geostrophic balance, that's what it's called, the geostrophic balance. Geostrophic balance refers to this tendency of our two main forces, the pressure gradient and Coriolis force, to come into a balance, to cancel each other out. So the word here, just sort of deconstructing this word, geo, of course, means earth. Strophic refers to flow. And so this refers to putting these two things together means flow on the earth. That's sort of what this word is meaning, flow on the earth. And in particular, it's really the slow flows that show this property, the large-scale flows. Okay, so if this is true, if the forces are roughly going to cancel each other out, it turns out this puts some pretty strong constraints on the kinds of flows that you can see at large scales. So let's sort of see if we can flesh this idea out a little bit. And for a specific context, let's suppose that we are looking at a pressure map. So this could be a surface pressure map where we're looking at isobars. It could be an upper level chart where we're looking at height contours. So let's suppose maybe it looks something kind of like this. So generally speaking, I've got the sort of basic steps in the argument listed up here, and I'm going to sort of draw them out under here down below as we go through the steps one by one. So first thing, sort of the starting point, is that we've got a pressure map here with higher values to the southeast, lower values up here to the northwest. And this could be a surface pressure map, in which case this is actually pressure. We're looking at isobars, or it could be an upper level chart. So either one, same kind of idea. Height contours or isobars, depending on the kind of map. Now, what this pressure map is telling us is it's giving us information about the pressure. And so the one thing that we can infer from that, based on this in terms of the forces, is the PGF, right? If we've got information about pressure, we can figure out the pressure gradient force. And if you remember back a couple screencasts, we have rules about how to do that. So let's suppose we're interested in this point right here, and we're trying to, right here in the middle, and we're trying to diagnose what the flow looks like at that point based on the information that we have in terms of the pressure. Well, the starting point, which is number 1 up here, is that we know that the PGF always acts across the isobars perpendicular from the higher side to the lower side. So our pressure gradient force is going to push from higher to lower across the isobars perpendicular. Important point here again is that it's always across the isobars perpendicular. Okay, so that tells us about the PGF. Now the second point here is just this thing that we argued on the last slide, which is that when you look at large-scale flows, most of the time you find that the Coriolis force is roughly in balance with the PGF. So if the PGF is pointing in one direction, the Coriolis is going to point the other direction and have roughly the same size. So in the present case, that means Coriolis is pointing towards the higher pressure across the isobars. So our two forces are roughly in balance, pushing and pulling in opposite directions. And now, the third step in the argument here is that if I know the Coriolis force, I also know something about how the winds are related to Coriolis. So if you remember back to our discussion of Coriolis, Coriolis acts to the right of the wind, meaning that if you have the wind at your back and you're looking downwind, the Coriolis is always going to act perpendicular to the right of that direction. So the Coriolis force is always acting perpendicular to the right. So on this particular figure here, if I'm standing at this position and I want the Coriolis force to my right, I'm going to have to be facing this direction in order to get Coriolis to my right, which means that the winds in this case are going to have to be in this direction along the contours here. So that if I'm standing at this position and looking in this direction of the wind is at my back, and I'm looking downwind, Coriolis will be to my right. So that's basically how it works. If you're given a pressure map, you can infer the PGF from the pressure information. You know that the Coriolis force is roughly in balance at large scales, as long as we're looking at large scales. And then finally, if I know the direction of the Coriolis force, since the Coriolis force is perpendicular to the wind, that also tells me the direction of the wind. And if you go through that argument, what you find is that the wind always is going to have this relationship to the isobars and or height contours. That is, the only way this is going to work is that the wind is always going to have to be along the contours in this direction with higher values of pressure or height to your right in the northern hemisphere. So the end result here is that the winds are parallel to your contours. The winds end up being parallel to the contours in order to get all the directions to work out right. Now this is kind of a weird thing because when you do other kinds of fluids, if you're looking at flows at smaller scales, for instance, or if you're looking at flow past a car or whatever, or an airplane, you don't expect this kind of thing. In fact, most of the time what you get is that the winds go from higher pressure to lower pressure because that's the direction that the pressure gradient pushes it. But that's not what happens at large scales. At large scales, the forces tend to come into balance. It takes a while, but they equilibrate. And once they come into balance, the winds, instead of being across the contours, end up being along the contours. It's kind of a weird thing. You get your winds being along the contours with higher values to the right. Let's go through and do a couple examples of this, because it's something that we're going to see over and over again as we move forward, so we kind of want it to be second nature here. So let's suppose we're looking at a contours on an upper level chart. So let's say it's the 200 millibar upper level chart. Just to be concrete. And you'll remember that when we look at upper levels, the contours are actually representing the height of that pressure surface. So these are our height contours for the 200 millibar surface. And let's suppose that we have higher values of the heights to the south, in particular to the southwest in this case, and lower values to the north, northeast. And again, this is typically what you see, right? Your surfaces have higher values where it's warm here in the south, and then they slope downward to where it's cold here in the north. Okay. And let's suppose that we're interested in this point right in the middle and see if we can diagnose which direction the winds are just from the height information. Well, the steps are going to go just like on the last slide. If we know information about the heights, that actually tells us about the pressure gradient force, because the pressure gradient force points perpendicular from higher values to lower values. So PGF is going to be something like that. Say, large scales, Coriolis force comes into balance roughly, so Coriolis force pulls the other way, roughly the same amount. Kind of like that. And then we know that the Coriolis force is to the right of the wind direction. So if I'm standing at this point, if I want to get the Coriolis force to my right, I need to look that way. So that's the wind direction. If I'm standing at this point with the wind at my back, looking downwind, then the Coriolis force will be to my right here, which is what we need. And so the end result, just like on the previous slide, is that the Coriolis force. The end result is that the winds end up following our contours pretty closely here, following the contours. And specifically, they follow the contours with higher values of heights to the right, looking downwind. Okay, let's see what this looks like on an actual chart. So this is just an example upper level chart. Looks like this is a 200 millibar chart. Just a random chart from a while back. And so let's see if we can diagnose what the winds look like just based on the height information. So again, the black lines here on the chart are showing heights, with higher heights to the south, lower heights as I go to the north. slopes downward towards the pole. And let's suppose that we pick some point here on the chart. Let's suppose we pick this point here. And let's diagnose what the wind direction would look like. Well, so again, pressure gradient force points across the isobars, or in this case, the height contours, so perpendicular, and pointing from the higher values to the south towards the lower values to the north. So like that, from the higher values towards the lower values. At large scales, so it's across the contours here, high to low. And at large scales, the Coriolis force roughly balances, so that's going to pull the other way, roughly the same strength. And again, if we're at this point and we want to get the Coriolis force to our right, we need to be looking along the contours towards the northeast. So that's our wind direction. So that Coriolis force pulls to the right of the wind. Now, we haven't really talked much about how to read the winds on the upper level chart, but if you look in the background here, all of these little things that look like little arrows and feathers are actually showing the winds. And the winds are actually going from the feather side here towards the tip of these little lines. So from feather to tip. So it's just like they're little arrows flying through the air. And if you look at all these guys closely, you see that most of them are following the contours pretty well, just like our argument should suggest. Right? We, based on the argument involving the forces, we argued that the winds should be along the contours. And that's a pretty good, it's a pretty good rule of thumb here. So pretty much everywhere along here, these arrows, these feathers and tips, are following the contours pretty closely. Now, it's not 100%. There are going to be places where it's not quite tangent to the contours because the forces aren't 100% in balance, but it's pretty close, especially at upper levels. Even as you follow some along the, along these curves and the contours, you see that the wind is pretty closely following these contours here, all the way around. Now, one of the consequences of this is that it sets limitations on the kind of flows you can have around cyclones and anticyclones. So for instance, let's suppose we have an anticyclone, or cyclone. Let's start with the low pressure case. Let's suppose we have a cyclone here at the ground. So these black lines then are showing isobars. And if you pick some point here on this, in this cyclone, along one of the isobars, because it's a low pressure, you find that the PGF is going to point across the isobars in towards the lower pressure, right, high to low, which means the Coriolis force points outward. And if the Coriolis force is pointing outward, to get the orientation with the wind correct, the wind actually has to be pointing towards the north in this case. So if you're standing here and facing north, Coriolis will be to your right. And you can do that at every point around the cyclone. And what you find then is that at every point along the cyclone, the winds have to be rotating around the cyclone. And they're rotating around in the counterclockwise direction here. Rotating around the counterclockwise direction. So what we infer then is that flow around low pressure systems, low pressure regions, tends to be counterclockwise. Flow around low pressure regions tends to be counterclockwise. Flow around low pressure regions tends to be counterclockwise. So we give a name to this kind of flow because this counterclockwise flow is associated with cyclones, with low pressure. We call it cyclonic flow. Cyclonic flow. Cyclonic flow is counterclockwise flow around a low pressure region. Okay, now if we go to an anticyclone, we go to a high pressure region, everything's going to flip because now we have higher pressure in the middle. So the PGF points across the contours towards lower pressure, which is outwards. Coriolis balances, so that's inwards. And in order to get the Coriolis force to the right of the wind now has to be to the south. And you can go through and do that same argument at every point around your anticyclone. And what you find is that around the anticyclone, the winds are circulating clockwise. So flow around high pressure regions tends to be clockwise. Flow around high pressure regions tends to be clockwise. And again, because that kind of flow is associated with an anticyclone, we refer to it as anticyclonic flow. Anticyclonic flow. Anticyclonic flow is clockwise flow around a high pressure region. So the end result then is that around cyclones and anticyclones, the winds tend to circulate around them, and the direction of the circulation is such that around a cyclone, you tend to get counterclockwise, and around an anticyclone, you tend to get clockwise circulation. Now, I should note that there is one assumption behind all of this. We've been making this same assumption all the way through this screencast. And that assumption comes from the fact that at each of these points, I've been diagnosing the winds so that the Coriolis force is to the right of the wind if I'm looking downstream. It has to be perpendicular to the right. But if you remember back to our discussion of the Coriolis force, that actually was only true in the northern hemisphere. So the qualifier here is that this was only true in the northern hemisphere. In the southern hemisphere, it's going to be a little bit different because instead of being pulling to the right, the Coriolis force points to the left of the wind direction, which essentially means that you have to turn around and look south so that you can get the Coriolis force to your left, which means the wind would be the other way. So I'll let you think that through, what switching to the southern hemisphere would do to these two different things here. For the moment, I'll just point out that unless I state otherwise, we're just going to say everything that we look at from now on is northern hemisphere case, just to keep it simple. And you can, if you have to, you can, in a specific case, you can always go back and think about what it would mean in the southern hemisphere. But it's going to be too complicated if we try to do both for everything. So just from now on, everything's going to be northern hemisphere unless stated otherwise. So here's an example from the text showing a cyclone. This is probably actually, I'm not sure actually what this is, whether this is a cyclone or a hurricane, just looking at it. It's a little bit hard to tell. I'm guessing it's probably a hurricane. But regardless, it's a low pressure center here. And so around the low pressure centers, as we just argued, we tend to have counterclockwise flow, cyclonic flow, around the low pressure center. And you can see that here in the cloud contours as they're sort of pulled around and spiraling around into the low center. So they circulate around the low counterclockwise. Now, of course, that's what it looks like in the northern hemisphere. Just for balance, we will show one case here for the southern hemisphere. And remember, in the southern hemisphere, the direction of the Coriolis force switched, which in the end means that the direction of the flow around the cyclone actually switches as well. And so for the southern hemisphere, it ends up looking something like this. If you have flow around a low pressure zone in the southern hemisphere, it actually ends up going in the clockwise direction. It just flips. Now, again, as I said, we're not going to spend a lot of time thinking about the southern hemisphere case, but I just wanted to show one example of what that looks like. I will point out that while the flow direction changes, the terminology we use doesn't change. A low pressure center, regardless of the hemisphere, is still going to be a cyclone. And the flow around a low pressure center, regardless of which direction it is, depending on the hemisphere, is still going to be cyclonic. So this is still cyclonic flow because it's flow around a low, even though it's going the other way because it's the southern hemisphere. But of course, things are never quite that simple. And the reason I say that is because there's actually one additional force that we haven't talked about yet. If you remember way back when we first started talking about the forces and we listed the forces that we were going to have to deal with, there were actually three. There was our pressure gradient force, there was the Coriolis force, and then we had friction. Friction was our third one. And the reason we haven't talked about it yet is because friction is typically the less important of the three forces. I guess grammatically that should really be the least important of the three forces since there are three. But you know what? This isn't a writing course. This isn't a communication course, so I can say whatever I want. Friction is the less important of the three forces. And I mean that in two ways. The first way is that the friction, even when friction plays a role, it's typically quite a bit smaller than the other two forces. So pressure gradient and Coriolis force are still dominant, and then friction plays sort of a smaller role. But the second reason that it's the least of the three forces is that it turns out that friction is really only important down near the ground. Friction is really only important down near the ground. And the reason for that is because most of the stuff that's causing the friction is associated with the air moving past the ground, and all that stuff is going to happen down at the lowest levels. Now, it does distribute through the atmosphere a little bit, but still, the effects of friction are going to be limited to some layer down near the ground. Just to sort of put a typical number on it, we usually say about 1 kilometer. So the friction is important sort of in the lowest kilometer of the air down near the ground. So friction is important at low levels in the atmosphere, about 1 kilometer or so or less, but not so much at levels above that. So if you're looking at a surface map, surface pressure chart, you have to think about friction. If you're looking at an upper level chart, not so much, because above 1 kilometer, there's not a whole lot of friction. Now, I'll note in passing, I actually said this when we listed our forces too, but I'll note in passing that what we're calling friction here really isn't friction at a fundamental level like you have if you are sliding down a slide or something like that. Because the friction associated with the air moving past itself turns out to be pretty small. But it turns out there are other things that behave like friction that kind of have the same impact on the flow that friction does. And in particular, turbulence. So turbulence here has effects on the flow that are very similar to the effects of friction. So what we're talking about here in terms of friction at low levels is really turbulence down near the ground, and that turbulence is behaving in the same kind of way that you would expect friction to behave, as it turns out. Okay, so what does friction do to the flow? Well, let's suppose that we start with a flow configuration without friction. So the same kind of thing that we diagnosed previously. We have high pressure here on one side, low pressure on the other. We've got our contours here. Since friction is only important at low levels, we'll say these are isobars on a surface map. And we've got our pressure gradient force pointing from the higher side to lower side across the isobars, Coriolis roughly in balance, and then the winds are along the contours. So this is exactly what we diagnosed before we added friction to the problem. So let's think what happens to this configuration if we add friction to the flow. Well, intuitively, what you'd expect to happen when you add friction is that it's going to cause the wind to slow down a little bit, right? Wind is air moving, and what friction does is it slows the motion down a little bit. So the first effect of the friction is it's going to slow the wind down. So I've got a bunch of overlays here on this figure. So when I go to the next overlay, you'll see the wind gets smaller. That's the first effects of the friction here. Here, I'll do that again. Wind was faster, but when I added friction to the problem, it slowed down a little bit. Okay, fair enough. But we also know that the winds are related to the Coriolis force, or vice versa. The Coriolis force is related to the wind. And one of the rules about the Coriolis force is that it's proportional to the strength of the wind. So if the wind slowed down a little bit, then the Coriolis force is going to get a little bit weaker. So that's step 2. Weakens the Coriolis force because the wind slowed down. In terms of my figure down here, I'm going to make the Coriolis force here a little bit smaller. So, boom, Coriolis force got smaller. Here, I'll do that again. Coriolis force got smaller. Boof, because the wind slowed down. Okay, fair enough. I slowed the wind down, the Coriolis force got weaker, but by making the Coriolis force weaker, now my forces aren't in balance anymore. Before, the Coriolis force was roughly balancing out the pressure gradient force, but now the Coriolis force is a bit weaker, and so the pressure gradient force is dominant. It's stronger than the Coriolis. And so as a result, the pressure gradient force is going to win the push and pull here. It's going to end up pulling the winds a little bit more strongly towards the low pressure. And so instead of being along the contours, the winds are actually going to veer a little bit across the contours towards lower pressure. So kind of like this. Oh, that's actually saying what I just said. PGF ends up dominating and the wind veers towards lower pressure. And it looks kind of like this. Poof. I'll do that again. So the Coriolis force was weaker. PGF ends up winning the battle, and so it ends up pulling the wind a little bit across the contours towards low pressure, and it looks kind of like this. Poof. You'll note that as I did that, the Coriolis force rotated too, because the Coriolis force has to be perpendicular to the wind, so if the wind rotates, the Coriolis force has to rotate as well. Here, so I'll do it again. Wind and Coriolis force both rotate together. Okay, so let's step through that argument one more time here, looking at the figures. So let's go back. Boom, 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 boom. This is our configuration if we don't have friction. This is still fine as long as we don't have friction. So if we're above 1 kilometer, this is what our configuration looks like with the forces and the winds. But if we're below 1 kilometer or so, then what happens? Well, the wind slows down. Boof. Because the wind slows down, Coriolis gets weaker. Boof. Because Coriolis is weaker, it's not in balance anymore, and the pressure gradient dominates and pulls the wind towards lower pressure. Oop, too far. Towards lower pressure. Jumped too far ahead there. I guess I should do this again. So, wind slows down, Coriolis gets weaker, and because Coriolis gets weaker, it veers towards lower pressure a little bit. PGF dominates. So the net effect then, the end effect of adding the friction is that instead of being strictly along the contours, the winds actually get pulled a little bit across the contours towards lower pressure. The amount that it's rotated here depends on the conditions and what's going on, but typically you tend to think 15 to 30 degrees. It'll end up being rotated across 15 to 30 degrees. So as a first guess, you can still say along the contours is still a first guess, but it's really going to be rotated a bit from that towards lower pressure. Now I will say one other thing. I probably should have said this on the previous slide, but I've been saying 1 kilometer is the depth where friction is important. That actually varies quite a bit too. At night it actually shrinks down really low to a few hundred meters. And then on a warm summer day, it could get up to 2 kilometers in some places, maybe even a little bit more. So 1 kilometer is just sort of a rough number, but it can actually vary quite a bit around that. So maybe up to 2 kilometers down to only a few hundred meters, depending on conditions. Okay, so this is most important on surface maps because it's important down near the ground. And so that means that we should think about what this means for cyclones and anticyclones on our surface maps. So let's suppose we've got a low center, a cyclone here, and we're thinking about the winds. Well, from before when we diagnosed this, the winds were going to end up being counterclockwise around the low center. That's still true, but because we're adding friction, they're not quite going to be along the contours anymore. Instead, they're going to veer a little bit towards lower pressure. And so the end result is you're going to end up with something that looks kind of like this. roughly along the contours in the counterclockwise direction, but veering a little bit across because of the effects of friction. And if we think about the anticyclone here, well, the anticyclone, the flow around it was clockwise. That's still going to be true, but instead of being strictly along the contours, it's now going to veer a little bit towards lower pressure. But since this is a high pressure zone, towards lower pressure is now outwards. It's now outwards a little bit. So our winds are going to be clockwise, but veering outwards across the contours a little bit towards lower pressure. So, one way to characterize this is that around cyclones, the effect of friction is to introduce a little bit of convergence of the wind into the cyclone. It's still spinning around, but there's also a little bit of a tendency to converge into the low center because you're crossing the contours. On the other hand, around an anticyclone, you're spinning around clockwise, but there's also a little bit of a tendency to diverge out away from the high center as you're spinning around. So around the cyclone, you're spinning into the low. Around the anticyclone, you're spinning away from the high. And then down here, final at the end here, I've got just a reminder that this is only, the friction is only going to be important down near the ground. So as a rule of thumb, about 1 kilometer or so, although it can be a little bit more or a little bit less than that. So if you're looking at a 500 millibar chart, you don't have to worry about friction. If you're looking at 200 millibars, you don't have to worry about friction. It's only down near the ground.